Can we beat the exact solution of the quantum harmonic oscillator with a smart guess? Let's test the variational method on the ground and excited states. And of course, we're definitely going to need our tables for this one. In this problem, 8.17, we're tasked with A. Use a trial function of the form psi of x is equal to a cosine of pi x over a between negative a over 2 and a over 2 to obtain a bound on the ground state energy of the one-dimensional harmonic oscillator. What is the best value of A? Compare the Hamiltonian minimum with the exact energy. Part B, use psi of B equal B, or psi of x equal B, sine of pi x over A on the interval negative a to a. A little different from what we had with the cosine, to obtain a bound on the first excited state and compare the exact answer. So we've seen this setup before with the infinite square well last question. This time it's with the harmonic oscillator, but the same questions and approaches matter, and this is why we care, because should be a great approximation. We'll see if it is anything compared to the success of the infinite square well, but with that, I'm still curious about how close can we actually get with some of these trial functions. As we remember with the Hermite polynomials and so on and so forth, the harmonic oscillator is not exactly an easy comer of solutions, but one of the most important. And for this question, you're definitely going to want to reference the PDF because a lot of the nitty-gritty algebra is left out of the video because it would just become monotonous. And as soon as you see how to do it in Part A, at least the landscape, Part B will follow suit very, very quickly. That being said, if you find value in this content, you can make a big difference by liking, subscribing, sharing it with a friend, or donating through Buy Me a Coffee. No account needed. Your support means the world to me and helps keeps this journey going. So onward with this particular journey of the harmonic oscillator. All right. As always, this setup only works if we have a normalized wave function. So let's set up and normalize. Of course, we plug everything in here, so we just get the magnitude squared. Fine, we're all real, and we're just going to assume that the magnitude A will stay put for now since we're not worried about phase factors. And if we want what from 0 to a over 2 is, or just some indefinite integral of a cosine squared with some coefficient on the x rather, then we could reference the Chalm's mathematical handbook and formulas, and this is the equation number that you would want to reference. Of course, with that, we set up the antiderivative and then plug in our boundary points, making it to where you have a 0 down here just kind of eases up on all the plug-in, and we know that sine of 0 and x of 0, just don't have to worry about this latter term. And then, of course, with the 2 and 2 and a canceling here from the a over 2 boundary, sine of pi, which reduces right there, that goes to 0 as well. So we're really just left with a over 2, and then that 2 and that normal, or the doubling of the integral 2 cancel, and so we're left with magnitude a squared, a over 2. Really not bad, all things considered. Go ahead and push it over to the other side, and then we see that a is equal to the square root of 2 over a. And again, we've seen this normalization constant before with the infinite square well, so we're very familiar with how this is supposed to look, but let's see if it has any carryover. Alright, so splitting up the Hamiltonian into its kinetic energy term and its potential energy term, since we know that the potential energy is going to be a little more difficult to deal with that x squared in it, we can go ahead and chop this up into two segments. The great part here is that the double derivative on cosine gives us back a cosine squared. So we're not necessarily having to do more work, we just have to be careful in it, because cosine goes to negative sine, which goes to cosine again. So the negative here canceled with the negative from the first derivative, and that's why we have a positive overall here. And then because of the chain rule, we have pi over a twice, hence the pi a squared on both of them. And then we see that we have a squared with our original function squared, and so we know that that had to be normalized, so that goes to 1. And so we're just left with pi squared over h bar squared over 2ma squared. Again, a very familiar setup here because that's what we had for the infinite square well. So we should be able to reference that, although clearly we can already see that this is probably going to divert a little bit from what the exact values were. But moving on to the potential term then, we see we have 1/2 m omega squared and then x squared. That completes the potential. But now we need to sandwich that with both of the with the magnitude squared, so psi star x squared psi, but then that all reduces down to a squared and cosine squared with the x squared from the potential. And now we're ready to go ahead and make a substitution on this thing here just to tidy it up. And then from there, we can use another table and clean up the integral. All right, so plugging in our normalization, pretty straightforward. If we let u equal the pi over a x that we had in the cosine argument here, make the substitution. This was our x variable. This would be dx, and then of course we change the limits. So that should be able to show us very quickly what everything is. The 2 and 2 cancel, easy enough. Then we have an a and a pi, but we have 3 of them. 2 from the x, 1 from the dx. So we're good to go there. And now we're left with a u squared cosine squared of u. And that's where we can reference our other table book here. Again, you could theoretically do this by parts twice, but I don't know why you would want to when you could just reference a table here. Much easier to deal with in my opinion. But we see that this is the antiderivative that we end up with. Again, you could do this from integration by parts, but why would you? I give you the page number and or the equation number and set. So you're good there. Now the task is to evaluate this at pi over 2 and negative pi over 2. The other thing that we can do to clean up here is that the a from the normalization and one of the a cubes from the substitution cancel out, so be on the lookout for that. And now we can go ahead and evaluate at the boundaries and clean it up. Okay, cool. So after all that's said and done and we evaluate at the boundaries, we see that the middle term goes to 0 because sine and cosine at pi over 2, especially whenever you go ahead and simplify the form, they evaluate to 0, so we're good just to get rid of that. And then we had the cosine at pi, cosine of negative pi, so that goes to negative 1 respectively. And so we see that we just end up with a duplicate here after we factor a negative out, and then the negative from the evaluation process turns that to a positive. So you get 2 of those, and both of them, after we multiply the 2 in, you get pi over 24, pi over 4, so we factor pi over 4 out. Hence, this pi is reduced to a pi squared from this one. And we get a 4 down here, so we're good to go there. But that cleans up the pi squared, that cleans this up to pi squared over 6 minus 1. And if you want all of those steps between here and here, check out the PDF because that'll save most of your questions. But for the sake of the video, you can see how we just kind of simplify it down. And thus, when we put this in together with the Hamiltonian and rewrite it in an algebraically friendly manner for the optimization process, we see that we get the pi squared h bar squared over 2. The a was down here, so we just put it to a negative power. All of this, and then we just have an a squared. And now we could take the derivative. The negative here comes out front for the power rule. So that's negative 2. That turns out to a negative 3. So we put it down in the denominator again. The 2 and 2 cancel, but the negative sign remains. So 2, bring it down. This 2 cancels with it. Here you just get a times 2 again. Remove 1 from the power, then you just left with a. That's what this is. The 2 from the power rule reduces with the 4 here. That's why we have a 2 there instead of a 4. And now we just need to set this equal to 0. And so we do so. Push this over to the other side. Thankfully, the negative sign makes that easy. And now we just need to multiply over the a cubed over here and divide off everything that is not a to the other side. Alright, so doing exactly that, we get this expression. And if we're smart, we can kind of reorganize it to where we have all powers of the same thing grouped together. That way, when we take the fourth root, everything can pan out nicely. Clearly, the fourth root of pi over 4 gives us a pi of a square, gives us 1/2 power because 2 over 4 reduces to half. So we can put that in a square root. And then this, you may as well just leave as the 1/4. But now that we have the variational parameter optimized, we need to plug that back into the Hamiltonian to find the minimum. And as we see here, a whole lot of canceling happens. Take your time with this step and make sure that you're comfortable with it all, because it clearly is probably the hardest part of it all. The pi cancels, h bar cancels, this m and that m cancel. This omega will be turned into the numerator due to dividing by dividing by a fraction, multiplied by the reciprocal. That's why we see it here. On the potential term, mass, 1 omega factor, that omega factor cancel, omega or the h bar stays untouched. Pi squared goes by, and we're good to go. Noticing here that this is 2 times pi squared over 6 minus 1, the same factor that's in the blue here, so we push it into the square root by putting it as a square first. So that factor and one of these factors will cancel, and we're in a pretty good position. Notice how both of these have an h bar omega over 2, h bar omega over 2 times 2, so we can factor that out, and in doing so, we'll be left with the 1/2 here, which we'll shove into the square root. And then what we'll realize is that we have 2 duplicates here, and that'll make our lives easy. All right, so here's that 1/2 I was promising you. If we push that into the square root, that turns that 1 over 2 into a 1/4. So this 2 and that 2, that is now a 4, will cancel down to a 2 overall. And so with that, we have this fraction, or this thing, over 2 for both terms. So we have a duplicate, so we have 2 of them. And now we put that 2 into the square root, and then that turns it to a 4 over 2 overall, and that leads us to a 2 inside. So that's how we have a simplification down to h bar omega over 2 pi squared over 3 minus 2, which when you do the numbers on this goes to about 1.136. And again, there's a whole lot of jumble that I'm talking about with the simplification here, but go check out the PDF because I have it literally step by step. Not always easy to see the path, but just trust the algebra and let it simplify it for you. Again, we want the h bar omega over 2 to stay put because that's what's going to allow us to compare to the ground state itself. And so by doing so, we see that we get an extra factor of 1.136 here, which of course is greater than 1. So we know that we are greater than the ground state energy, and we conclude that we have a 13% overage here. And that kind of makes sense based on the trial function, which, I get what they're trying to do here, trying to match the Hermite polynomials and how they coast along, but not always the greatest fit here, especially when considering everything else. And 13% is quite a big difference from the 1.3% we saw with the infinite square well. So kind of concerning there. As far as now, this part A is complete, but let's talk about some of the things that happened in it. Although we have discontinuities at the boundaries, meaning that the negative a over 2 and a over 2, because we were said that we go to 0 outside of that. The thing is, we don't have to worry about any delta functions or things like that because the function itself is 0 there too. So although the function is continuous, the derivatives we don't need to worry about due to 0, zeros happening at those spots. So we should be okay there. We don't have to do any other work like what we saw in the examples from the book, but still a great thing to keep in mind when we're worried about continuity between the conditions and the endpoints. And then that concept leads us straight into part B, which is stop number 2. And we realize here that this can only work, which we saw at, I think, question 8.4, where if the trial function is orthogonal to the ground state, then we're okay. And in this case, the trial function initially was even because it's cosine, and sine is odd, so clearly the overlap there will cancel over the symmetric domain, so we're fine there. And then if we want to use this now for the first excited state, then we need to bring into again account for the normalization factor. And as we see, we just plug in magnitude squared, all the fun stuff. And this again leads us back to a sine squared of some coefficient on x, which we can get from the Shams outline table. And so we can go ahead and find this pretty quickly. Again, it's actually pretty even or pretty consistent with the cosine, meaning that everything is the same except now you just have a minus sign. Pretty helpful there. But once again, a little bit of inspection can help us. We realize that we have sine evaluated at 0 on this endpoint. So sine of 0, 0, that thing's 0, 0 over 2, 0. So that whole right side of the boundary is 0. And then this one here, we get 2 pi over a times a. Well, the a and a cancel, so you're left with sine of 2 pi. So this whole thing's 0. Save yourself the trouble now. Just get rid of it while you can. And thus we're left with a over 2. And as you see, doubling the integral here to put the 0 in the limit saves us time. 2 and 2 cancel, so we're left with b squared a is equal to 1. And that's what we see here. Clean that up. So the normalization factor is 1 over square root of a. Very, very similar to what we saw last time, so we don't need to worry too much on the technicalities, but very easy to use forward. Again, we're going to kind of use the segue from the fact that we have two derivatives here, and that in the sine cosine relationship, we end up with the negative somewhere. So the negative from the derivatives cancel out with the negative from the kinetic energy operator, and thus we just get another what was it? Chain rule factor here twice. So pi squared, a squared, and then we see that b squared with our original function. That equals 1 since we normalized it. And again, we get pi squared h bar squared over 2ma squared. Again, this looks very much like the finite or the infinite square well and everything that has its energy. So it makes reasonable sense why these things don't exactly, pair well when it comes to the error analysis. So at least you're being consistent if you get the same line of thinking from these same constants. All right, well, moving on. We have the exact same setup as we did for the first trial function, except now we have sine instead of cosine squared. And we're over negative a to a. So let's do the u sub again. Get this down to something easy to deal with. And that puts everything a pi over a pi. We have 3 of them. As you see, the a cubed and this a will cancel. Good to go. The integral, of course, takes the same form as we saw for the cosine, except now we have a minus and a minus. That's pretty clever. I know that back when I was in undergrad, one of my professors was like, "Yeah, there was a whole series that someone went through a book pretty much like this, improved all the integrals." So I'm gonna have to go find that so that I could share it with everyone. But this table of integrals and knowing how to prove them, you never think you need it until it's right in your face. And having something like this table is very, very helpful. You just don't know. And trying to rely on something like a symbolic engine like Mathematica or Symbol Lab sometimes fails you in that process. So having something of a hard copy like this would probably be a good investment if this is what you want to do long term, because trying to memorize them all is practically useless. Knowing where to find them, how to find them, and having the intuition on what a possible solution might look like, that's what you would need. So enough of that ranting. We see that we need to evaluate these at plus pi and negative pi, and that'll be simplified relatively quickly because that sine term again will go bye-bye. All right, so again, sines don't like pi's, so we get rid of that and that. And then we had, what was that, cosine of 2 pi, cosine of negative 2 pi, so we get a 1 and 1 there again. Again, we see that we have a duplicate here, so we have a 2 that gets pushed out. So that's 2 and 2 cancel. And then we see that we're going to try to factor out this pi over 4. So to make that a 4 there, we multiply by 2 over 2, and hence the 2 there. And when we do that, we cancel the factor of 2 times 3 and a 4 times 3. So this gets to a 3, and we're good to go. Again, the pi that we factor out reduces this 3 to a 2, and then we get a 4 down here. So we're doing pretty good. Looking pretty darn similar to what we had last time. Hamiltonian, pretty much the same thing. The only thing that changed was this bracket. Go ahead, take the derivative. Same pretty much setup. And now we have to set that equal to 0. And as you saw from part A, we should be able to do that pretty quickly. All right, so isolate A, push everything that isn't A to the other side. Again, same setup, just different from the bracket. And now you see that we have the optimized A. Same form, except now this thing is not pi squared over 6, it's 2 pi squared over 3. Slightly different, so hopefully this will give us a better error analysis. Again, when you plugged it into the Hamiltonian to make it the minimized version, we see the same cancellations. The only thing that changed was this 2 pi squared over 3. And let's see how that simplifies down and what error we might get. All right. So now we want to factor out the h bar omega over 2 out front. Go to tidy it up as much as possible. And as you see, we know for the first excited state, we had 3 halves, 3 halves h bar omega. So we factor that 3 out. And we clearly see that 3.34 is bigger than 3. So that tells us that we are, again, a greater bound, but we're looking for the lowest greater bound. And actually doing this, we see that we get an error of 11%. So it's definitely a little better, but still not ideal. Clearly, if you're just trying to get a ballpark, you could definitely program something to solve these integrals very quickly, all things considered. And then you'd be in a good situation. And again, 11%, not that bad if you're just trying to get a quick ballpark, but just not that great either. But again, if you're just trying to highlight what's going on, instead of dealing with those Hermite polynomials and all that weird stuff that we saw back in chapter 2, this might actually be beneficial for just trying to see if you're even in the right range for the lab experiment, if that's what you're doing. If not, just another great example of how to use calculus with our, one of our most powerful models of the simple harmonic oscillator. Whew. So, now you get to see a flashback from chapter 2 of both the infinite square well and the simple harmonic oscillator, and that was quite refreshing to see that we can actually see how different models affect the different atmospheres of error that we see. It was very quick to see in the infinite square well how you were trying to match everything insofar as a Taylor series approximation to the actual sine function, and with just a couple polynomials, that was able to happen. The harmonic oscillator, not so much. So, but all that being said, thank you again to all the supporters of the channel. You make this possible. I can't wait to get into some of the other stuff like the quantum dynamics in chapter 11 as I'm kind of reading ahead. But I think this will be a fun thing to get into. That being said, all the books and notes on this will be linked below because clearly we're seeing the value of those integral tables, so definitely grab them while you're here. And of course, if I find any more, I'll either put them in the Instagram um, group chat thing, whatever they want to call it, broadcast channel, or just put it in a Patreon group, whatever works. If you have any questions, please feel free to reach out. As always, thank you for watching, and until next time, stay curious.